presentations for the class in Human-Centered Robotics. I know you guys have done a terrific effort in the last few months. We'll have very interesting project presentations today.
Hi, my name is Jack. I'm a senior in the Department of Biomedical Engineering.
And my name is Emily, and I'm a senior also in the Department of Biomedical Engineering.
So basically what we're doing here is to build a flexible tactile sensor that's based on fabric and is able to sense pressure. So the materials we use are very simple, and they're mainly just the Biostat, which is the piezo-resistive material, and also the neoprene, is synthetic rubber, and also the conductive thread. And with those materials, we're able to make kind of pressure sensors out of it.
And you can also play multiple notes at once. But you can see there's a variable pressure as it increases, and pressure increases in volume.
My name is Sandeep Yayati. I'm a master's student in mechanical engineering.
And I'm Megan Vaughn. I'm working on a PhD here in mechanical engineering.
The goal of our project was actually to create a Biomedic robotic knee joint, so mimicking human motion in the knee with a mechanical and electrical system.
So what we ended up doing is realizing that the human knee is capable of a whole lot more than a robotic knee right now. All of us walk around, we run, we jump. So by looking at the human knee, we figured, hey, we can come up with a really good design for a robotic knee.
So we can basically command a position here, and it'll just go there. You can see here is kind of where our set point changes, and that's the leg traveling to that position. You can imagine the possibilities with something like this in prosthetics, in robotic designs in the future, as you can iterate on it, could be pretty beneficial.
Our project is related to modeling and simulation of below knee amputee prosthetic control. Below knee amputees have lost their ankle muscles, so they are able to use these in running and walking. And these muscles are very important in the subtasks of walking, for example, propulsion, which would propel the body forward and develop walking speed, as well as initiating swing of the leg. Our goal was to simulate different control strategies in controlling these active prosthetics using novel sensing technologies, for example, inertial sensors that you can place along the body, pressure sensors on the foot, as well as electromyography to measure muscle activity.
We were able to investigate how different control strategies influence the dynamics of below-knee amputee walking, as well as through dynamic optimization, evaluate how an amputee would have to modify their existing activation patterns for a specific strategy. And so basically we started off with an existing control simulation of a non-amputee on the right there. And as an example, our amputee simulation on the left was able to reproduce the same movement with one of our control algorithms as the control simulation, as well as same ground reaction forces and ankle torques.
My project for the semester was to build a prototype using these new compliant fluidic muscle actuators that hopefully will be used in the future on a robot. The actuators are set up antagonistic to each other, similar to a human muscle system. So one has to actuate for contraction, the other has to actuate for extension.
This is my project for the class. It's a torque-controlled brushless DC motor test bench. The motor is able to measure the angle of deflection on this arm, which is coupled to the motor shaft. And based on the angle of deflection, it will increase the torque generated by the motor. And the torque is measured by this torque sensor, which is in series with the motor and the end effector. Here, there's no torque at all, and as we increase, this is limited by the power supply at 3 amps, but you can see how there's quite a bit of torque being applied in the opposite direction.
We focused on taking humanoid robotics, but also thinking about how we could bring it to everyone. So our project has some interesting constraints of, we took an off-the-shelf product that's made by Lego Education. It's working one of their new Tetrics to try to make a humanoid-based walker that anyone could produce. So it initializes, and then it's going to look at, it'll actually go over and start to be able to do basic walking, as we'll talk about. It's a little slow at times. We have some different versions that we do to kind of see that simulation. But you really are always going to be looking at, it's basically always working on that shifting of the weight is where the biggest come in. But we really thought this project allowed everyone to kind of work with and see how you could move and work with that experience of looking at walking within a framework that anyone could do.
And our project was essentially to figure out what people are looking for in a social robot head. As robotics become more and more common, you're going to be interacting with them in your life, and we were wondering what type of robots people would want to interact with.
So this is the final solid model we arrived at. And there are various iterations. Obviously it started off very crude, and we found that varying the feature sizes would have a huge impact on the appearance, like especially the eyes and the nose. Just a slight change in the curvature would basically make or break the model. Then we added these eyelids and eye textures, and this helped a lot with the sophistication. And then the clay model is the physical manifestation of that.
Okay, that's great. So thank you very much for your projects. You guys have done a terrific job. I have enjoyed the class with each of you. I expected less, and you have given more. So an applause for all of you. Thank you.